Hello dear students, welcome to the channel and welcome to very new playlist in which we are going to discuss about the symmetrical and unsymmetrical fault analysis. We are going to talk about symmetrical components of power system. So today I'm going to discuss about the transient on a transmission line, and if time permits, then the short circuit currents and reactances of synchronous machine as well. So uh, let's get started. Before we get started, one thing I wanted to share that we have made the whole playlist on transmission line modeling and performance, which is also exclusively available on our YouTube channel. So if you haven't checked it out yet, if you want to know about transmission line and its modeling and performance analysis, please check it out. The link will be flashing on the I button on the top right hand side corner of your screen. So now we've talked about it, let's get moving and talk about symmetrical fault analysis today. First, uh, what is a symmetrical fault? So a symmetrical fault is a solid three-phase short circuit, right? uh, such faults uh, such faults are produced in the system because of insulation failure of equipment, or it can be faulty operation, right? uh, Accidental faulty operation, or it can also happen because of the flashover of lines, right? Because of the um, lightning stroke. So during such faults, there will be heavy short circuit current flowing through your system, and because of that, uh, your system can suffer from permanent damage, or your major equipment of your system can suffer through permanent damage. And because of that, system must be protected against such faults, against the flow of such current, because it can harm your system on a very severe level. And we can do it by disconnecting the faulty part of the system, right? It is very simple. We simply disconnect the faulty part of the system. And for that, what do? We use circuit breakers and protective relays. There are so many protective devices available for a whole your system, and in particular devices, like in particular sections as well. Like if you want to protect transmission lines, or if you want to protect your substation, we have mechanism for that as well. But it is necessary to estimate the magnitude of current flowing through your line during the short circuit condition, right? So you can select the accurate circuit breaker and protective relays, because if your protective relay and circuit breaker won't be very much accurate, then it will not be able to protect your transmission line or your substation or any equipment. So the short circuit currents are estimated by analyzing symmetrical faults, and though these faults are very rare, symmetrical faults you won't find them very occurring very often, but symmetrical faults leads to most severe fault current, and because of that your system can suffer severe damage, so it must be stopped. So now let's talk about the transient on transmission line. So let's consider this circuit which I've shown in the figure. A RL circuit, three-phase short circuit fault is taking place in this circuit. And before we do the analysis, we have to make a few assumptions. Like the first one will be the series RL circuit is fed from constant voltage source, so there is no breakdown, or there is no flicker or any change in my voltage source. And the voltage which is coming, what is the voltage? You can see here, Vm sine omega t plus alpha, right? Then the short circuit is taking place when system is unloaded, right? There is no load connected, and you can see that here in this figure as well, there is no load connected. The third assumption will be the circuit is presented by lumped RL circuit, which is also visible in this diagram. So to make the initial calculations, what we will assume that short circuit is taking place at time t is equals to 0, and based on that we will do the calculation. So let's do the calculation. Let's come to the calculation part. First, what we will do, we have to find the fault current, right? So what we will do, we will apply the Kirchhoff's voltage law here in this circuit. And as we have only just two equipments connected here, we only have a resistor and inductor here. So what will be the voltage across resistor? It will be I into R. What will be voltage across inductor? L di by dt, right? And the total voltage will be V, and V will be equal to IR plus L di by dt. But come here again and see what is the value of V. V is Vm sin omega t plus alpha. So we will simply replace V in this equation. So we will get IR plus L di by dt is equals to Vm sin omega t plus alpha. Now what do we want? We have to calculate the fault current. So we will come here and we will make I as subject. So when we will make I subject, my formula will look something like this. I is equals to Vm under root of R square plus omega square L square, which is nothing but my impedance, the line impedance, this one, into sine omega t plus alpha minus theta. See, we have added a new component here, which is theta, because of this because of overall impedance of my system, right? So we will come across that how theta is affecting as well. Actually, theta is nothing but difference between your transient and steady state waveform, transient and steady state angle. And we will come across that when we will see the waveforms. But for now, know that it is nothing but difference between those two. So based on that, we will write this whole term as Z. So I will be Vm by Z sine omega t plus alpha minus theta, right? Now we will what we will do, we will apply initial condition in my operation. So whenever we apply initial condition, what happens, we take the voltage is equals to 0. So the overall voltage will be equal to 0, which means L di by dt plus Ri will be equal to 0. And when we do that, we will send Ri on the other side. So L di by dt will be equal to minus Ri, and then what we will do, we will take integration on both the sides. Why we are doing that? Because we want to find the value of current, right? So in order to find the value of current, we have to take integration, because this one is in differentiation term and this one was not in differentiation form. So in order to find the value of current, you have to take the integration, so that you can bring it in its current form, and then you can integrate over it, right? So by doing that, by taking integration, we will find the value of I, and I will be A into e raised to minus RT divided by L. And then as this is an initial condition current, this is the current at initial condition, what we will do, we will add this value to the original value of I, to this value. So what was the original value of I? It was V max by Z sine omega t plus alpha minus theta, and we will add this value A into e raised to minus RT by L. So we did that here. Now at t is equals to 0 time, the value of current will be 0 as well, right? When t is equals to 0, that means your switch is completely open here, which means there is no current flowing through your circuit, which means I is equals to 0. So we will take I is equals to 0 and we will put it in here, and we will also take t is equals to 0. So what will be my equation? So 0 will be equal to V max by Z sine t is equals to 0. So this term omega t will become 0, alpha minus theta. So it is here 0 is equals to V max by Z sine alpha minus theta plus A e raised to RT divided by L. Now t is equals to 0, which means e raised to 0, anything raised to 0 is equals to 1. So we will be left with A only. So it will look like this. Now based on this, we can find the value of A, and to do that, let's make A a subject. So A will be minus V max by Z sine alpha minus theta. Now that we have found the value of A, we can also substitute value of A in this equation. the equation of I, and when we do that, we find this. This first term will remain as it is, but this term here, instead of a, we will put this one, this term minus v max by z sine alpha minus theta. So we will have minus v max by z sine alpha minus theta e raised to minus rt by l. Okay, and then instead of v max we can write root 2v if you want to. If you don't, then it's okay. There is no there's nothing wrong with that. You can do that as per your wish. So now this first component, the component with sine omega t, is actually my steady state component of my current, or you can also call it symmetrical short circuit current. Okay, and the second component which is getting subtracted from the first component, please note I'm putting emphasis on getting subtracted from the first term. That component is actually my transient component. Okay, or you can call it DC offset as well, and it delays the corresponding time, it delays corresponding of time constant. Okay, so now let's see how does it affects my system and how the current waveform will be shaped. So here we have my current waveform. You can see this waveform is my steady state current or my symmetrical short circuit current, right? So it is the part of v max by z sine omega t plus alpha minus theta. So this is v max by t sine omega t plus alpha minus theta. Okay, and this one is my transient part. So what is happening in this part? It is v max by z sine alpha minus theta e raised to okay, yeah, it is because of that whole part, not only the transient but the whole second term. Okay, the transient is this one, right? The transient is this one, and the third one is the summation of both of them. So this will be my sine omega t plus alpha. This is my sine omega t plus alpha. Okay, and then this is theta. Okay, so here you can see the difference between both of them. This difference between this peak and this peak is theta, and based on that we will get the value of my steady state current. So based on that we are getting the whole term as a resultant of both of these terms. We are getting Vm by z sine omega t plus alpha minus theta, right? So this waveform is omega t, this waveform is actually alpha. You can see the delay here, and resultant is that, and the whole term is v max by z sine omega t plus alpha minus theta. This term, second term, is my transient. As you can see here, it is root 2v by z sine theta minus alpha. Okay, or v max by z sine theta minus alpha. So this angle is that, and then we have e raised to minus r by l into t. So based on that we are getting this curve, and this is my transient current. And when we take both of them, or actually three of them, and then we add them, what we will get? We will get resultant, or my fault current I, which will be actually addition of is I steady state current and it transient current, and it will look like that. Okay, and again apologies, I think I messed it up a little bit in the first equation. Actually this is the waveform of current, and this one is the waveform of voltage. Okay, so initially the thing I was talking about will be this. right? And because of voltage, what was happening in voltage, voltage was V max, right? So this is my V going on here. Now coming to uh, this plots to momentary short circuit current, that IMM is the maximum momentary short circuit current, and corresponds it corresponds to the first peak of total I, which means this peak I'm talking about. So if the decay of transient current in the short circuit time is neglected, then you can write your equation of your current like this. It will be root 2 by z into V sine theta minus alpha, because we neglected the decay of transient current. So we will take plus root 2 by V by Z. There is no decay we are considering, so root 2 V by Z. And as the series RLC circuit corresponds to the transmission line, the resistance will be very small, right? And when resistance is very small, you can take theta close to 90 degree, right? Because the resistive component will be 90 degree apart from the inductive component when we draw phasor diagram. So you can take theta is equals to 90 degree, and based on that, as both of them are perpendicular, you are taking theta is equals to 90 degree, and because of that, what will happen, this sine theta minus alpha will become sine 90 minus alpha, and sine 90 minus alpha is what? It is cos alpha, right? So it will be root 2 by V Z cos alpha plus the second term as it is. And if the short circuit occurs when the voltage is going through 0, which means alpha is equals to 0, and when alpha is equals to 0, the cos zero's value will be 1, which means this term and this term are uh, basically the same term. So we'll have 2 root 2 V by Z as my maximum momentary short circuit current, right? So it is twice the maximum value of symmetrical short circuit current, and we call, because it is twice, we call it doubling effect. Okay, so this is doubling effect. Now moving towards the next topic I wanted to discuss is the short circuit current and reactance of synchronous machine on no load condition. So the power which consists of power system actually have so many components, right? Let's not jump to power, first discuss about the system itself. So power system has so many equipments, like we have synchronous generators, we have transformers, we have transmission lines, there are number of loads connected, so many things. So in abnormal operation of alternator, it is subjected to the transient condition, and this transient occur because of the switching operation or any sudden change in load. Basically if there is any sudden change in load, then this transient situation will occur, right? Any sudden short circuit can also occur. So these short circuit faults in system, they develop severe mechanical stress on my armature coil, and because of that, what will happen, it will produce some large torque which can be which can cause major damage to my armature or the prime mover of my armature. So the analysis of synchronous machine under short circuit condition is very helpful in predicting any possible conditions which are resulting from any abnormal operations. So in synchronous machine, always remember the uh, the armature and field winding are assumed purely inductive, and because of that, what will happen, the flux linkage in the armature and field circuit will not be able to change suddenly, right? By application of short circuit to my what you call armature winding. So the current which is flowing through armature of synchronous machine under short circuit condition will be same as the current which were flowing through RL series circuit, right? But there's the catch. What's the catch? um, in RL series circuit reactance, it was constant, right? But in synchronous machine, it is function of time actually. It will it will change according to the time. So under no load condition, we don't have any mmf, no mmf in armature reaction, right? So when suddenly this three phase short circuit will occur at the terminal of my synchronous machine, the current in armature circuit will increase suddenly to very large value. And because resistance of winding is very negligible compared to its reactance in armature, right? The current is very highly lagging, and because of that, what will happen, the power factor will become almost zero. So this sudden increase in armature current will now accompanied by armature reaction. Remember the fundamentals of armature reaction, right? So the sudden increase in armature current will be accompanied by armature reaction. And because air gap flux cannot be changed instantaneously, uh, to basically to counter the demagnetization of my short circuit current in armature, the current appear in the field winding as well as the damper winding in the direction to help that main flux. Okay. So what will happen, the uh, armature reaction under the steady state condition of my synchronous generator will produce some demagnetizing flux, right? So this short circuit current in machine will decrease, machine will decrease based on the winding time constants, and the damper winding will have low leakage inductance, and field winding will have large leakage inductance. And because of that, the time constant of damper winding will be less than the field winding. Now during the initial part of the short circuit, the current which was getting induced in the damper winding and field winding will be uh, will be because of the transformer action. And uh, because of that, what will happen, there will be reactances, different reactances will appear. The circuit model, in the circuit model, the reactances xf and xdw will appear in parallel with xa. Okay, here you can see, in this image you can see your xf and xdw are appearing in parallel with xa, as you can see here. And because of that, what is happening, this damper winding current, if first to die out, xdw effectively will become open circuited, and after that stage the xf will become open circuited, right? First this will become open circuited, then xf will become open circuited, and the machine reactance will change from parallel, which was actually in parallel from xf and xdw, as you can see in this image, parallel combination of all three of them during initial period of short circuit, and then xf in parallel in the middle period of short circuit, right? So initially all three of them were in parallel, right? xdw, xf and xa. Then what happened, xdw went off, and we will have xf and xa in parallel, right? And in the later stage, in the third stage, or this is in the middle, this is in the middle stage. Okay, so in the third stage, the first stage we will call subtransient, second stage will call transient, and third stage will be steady state, of course. So uh, in the third stage is shown here, the xf will also will go off, and we will left with xa only, the armature reactance only, right? So the reactance of my machine in the initial period of short circuit can be given by this formula. We basically had xl, and we are talking about the initial period, which means all three of them were in parallel, and the combination of parallel connection of them was in series with XL. So we will give it XL plus 1 by XA plus 1 by XF plus 1 by XDW, and the resultant will be called X double dash XD double dash, right? So it is subtransient reactance of your machine. And if you want to find the transient reactance, then we will call it XD dash, right? After the damping winding current will be died out, and because of that my XDW will be died out. So because of that we will have only two of them, XF and XA, and we will basically take both of them in parallel and plus XL in series. So this component will go off and two of them only will be remaining. And after that, in the third stage or the steady state, what will happen, XL and XA will be parallel, so XD will be XL plus XA, right? So the reactance under steady state condition in the synchronous reactance of the machine XD, and it will be nothing but the sum of XL plus XA, and obviously X double dash D will be less than XD dash, and the XD dash will be less than XD, which means the value of XD is the maximum and the value of XD double dash will be minimum, right? And because of that, machine will offer different reactances based on time, right? So that was your short circuit current and reactance of synchronous machine on no load. So we will conclude today's lecture here. If you have any doubts, any queries related to this lecture, please mention in the comment section below. I also want feedback from you guys if the speed of the lectures are too quick, if my speaking speed is too quick. So please tell me if it is too quick. I can so I can improve on it. If you have any suggestions, any feedbacks, they are welcome. You can mention in the comment section below. I will try to address your comments as soon as I can and as many as I can. So I will be seeing you in the very next lecture. Till then, take care of yourselves and goodbye. And again, thank you very much for listening.